Now we're going to listen about how to mine icy regolith, combining a slusher, a hoist, and IoT technologies in the lunar crater, excavated in your own backyard. So that's something for me, because I had intended to not do lunar ice mining. Victor Tenorio has been focusing on smart mining and decision support systems. He has been working in Lima and in Peru and Alaska Fairbanks. Currently a professor of practice at the University of Arizona and the founder of the Wildcat Moon Miners. That sounds interesting. Floor is yours, Vito. Oh, you need to unmute. Sorry.
Thank you very much, Niklas, for the introduction. I'm very pleased and very honored to be in this conference. I'd like to contribute a little bit with some mining ideas. That's not me. Basically, I will start with one of the practical ways. Okay, I'm back. Okay, one of the first practical ways to do mining on the lunar surface. This work is not new because I've seen this before in other documents, especially the work by Richard Gerst. Actually, this is my main source. I also saw this illustrations and concepts in David Litzler's book, Mining the Moon. It's a great reference for me, but I would like to not only honor that work, but update it, curate it, and also bring it down to earth. So I'm going to show some generic information that we already know and we have seen before, like the geologic map of the moon, and the fact that we are focusing on the South Polar region. This has been said before, because there is abundance of evidence of water and other materials that we may require, and basically for the regolith itself. Some economics of moon mining, which is a rather recent document, give us some values that I wanted to present here. The most important for this presentation is the moon surface. The demand will be something like 100 million tons per year at a cost of $7,500 per kilogram. And some of this will be for the habitat and for other foundations and things that we're going to require. And others, like the moon orbit, will be for the gateway, and the lower orbit, some other structure that we may need or orbiting this. Oh no, sorry. Excuse me. Thank you. Thank you. Screen 2, screen 1. Oh, I should be, okay, I'm sharing. My apologies, I'm going back just to the introduction. I haven't done anything there, like, and I'm going to the geology of the moon, as I mentioned. Yeah, thanks. And then the economics of moon mining. This is from Somariva, and I bought the reference at the end. Important thing is that we are going to require this number of tons. I expect that this work, which is very modest and small in amount of material moved, would cover more or less.
We still do not see the screen.
No. Oh, that's so bad. Let me try that again. Let me see if I can see this. Let me know. Okay, you should be seeing it now.
It's okay now. It's okay.
Thank you. Thank you so much. All right. All this is just introductory, and the geologic map of the moon, and this economics of moon mining. So the expectation is that the work that is being presented now will be covering at most 10% of this demand, and it's kind of ambitious, but at the same time it could be done if we replicate the work in several areas of the moon on several scenarios. There's some background information I'm using in this title slides, some AI concepts of doing the moon slusher. Is completely imaginative, but it's good as a reference. This also has been presented before, but I would like to to show it again as our neighborhood. Here, Shackleton and Malapert, and I've been having a kind of a couple of experiences with Break the Ice Lunar Challenge and also Rascal recently to have choose an area of interest close to the South Pole and therefore close to Shackleton. Here are some predefined sites, 1, 4, and others. I'm using this one, and I'll show you why. Because this is from Moontrek. This is the South Pole. The area of interest will be this. There are several areas of interest, perhaps more or 4 around the crater, but more important is that this is the line of the near side and the far side. And perhaps it's psychological or so, but I would like to see the air while I'm working here. Here will be not the same case, and that's one reason for starting. Also, all this area around Shackleton is full of small craters, and for sure they may have ejecta from the big Shackleton crater or the meteorite that may have produced this, and that is abundance of iron and nickel. So that will be also a good starter. Gerst's work was more generic, just collecting the regolith for melting or extracting the metals. I'm trying to focus first on the water and second on the utilization of the regolith for the habitat, for burying the habitat and so on. This is the regolith, and this is kind of not new, but has been made by Sound Velocity, and apparently this is the configuration of the regolith, of the stratigraphy of the moon. The powdery regolith that we know from the Apollo landings and others, and then the ejecta we were talking about with the metal pieces and so on, and other crust, that all of this would be harboring water in the South Pole. And then we go deeper and it will be harder. There will be other challenges for future presentations, like how to mine on the moon. The simplified stratigraphy was used by NASA for the Break the Ice Lunar Challenges, and I'm still using for it. I expect to have excavations with the Slusher near 5 centimeters or so. So we may have here 4 rounds, and here like 40 rounds or so, or more, 80 rounds or so. And here more, I don't know if the Slusher will be able to help us with that. The technologies that I'm using are very traditional, and I try to pay homage also to Greg Baden's presentation from yesterday. It was impressive. He was mentioning a lot of INCO, and my advisor, Dr. Sean Dasserold, developed his thesis on INCO in teleoperation and other things that are pioneer in the INCO mines. So in INCO mine, so this kind of connects the dots with all the things I was learning all these years. I'm showing something very vintage, but at the same time, it's important because we can transfer this, translate it to the moon. This is an underground operation, a stope, and this is a slusher. I use this in purpose because it's a little bit more complex than the linear slushing, but it has pulleys, and I have cables, and I have different directions, and in a safe mode, the operator can extract the material, scrape it and put it close to here. The rails are here, are ending up here, and we may have a minecart or more, or even a mucker, a pneumatic mucker. All this equipment is pneumatic, so it's also vintage, old school, but it's good because it's easy to fix and reproduce. And these are the graphs presented by originally by Gerst on the NASA's documents, but this illustrates, and I like to show this because it illustrates how it's going to be one of these pits. This is not necessarily a crater; it's a pit made by humans by doing the scraping or the slushing process, and it may have a sort of a ramp here. We may have scales and other IoT sensors that we'll talk later, and some sort of low-profile track that is very common in underground mining. But here we are in the surface, and we may have other craters or flat areas that we might want to exploit. Other graph that is like of the same documentation is the profile view, and the bucket is interesting because it's like a box with some particular weight and things that we need to use for doing the slushing itself. This is a graph. I don't have the source for this, but it's for the moon for sure. And this is the way the slope ratios can be done if we do a ditch or some sort of terrace or a pyramid of some sort, berms that are very common in surface mining, and how the material behaves. And this will be good as a guide for how to deal with the final profile of the mine. Translating again this in our backyard, Tucson, Arizona, I want to introduce the San Javier Mining Laboratory. It's a mine from the turn of the century that was exploited in 3 levels, and we still are a mine school and a laboratory. We're modernizing, we're using the Internet of Things, we're developing a digital twin. So, and it's only half an hour driving from University of Arizona campus to Sahuarita. We have a land already. I claim in this land for this work or some other area that we may use it. And first of all, well, we did this with a scoop tram, but we want to, we made the analysis, try to mimic the chart that I have shown of the typical angles that we might find there. The material is loose and it may or may not be a proper regolith simulant. However, I would like to bring slide. Oh, sorry, someone is writing something. Please, context maker. Tenorio speaking. Okay. All right. Yes, with this we might try to make them. There's other places in where we can get loose material that it may resemble a regolith simulant or buy a regolith simulant. I even want to paint it for the different layers, but then when it's all mixed up, I don't know how to put it back. But those are the down the earth things that we might need to deal with. This will be more or less the area. I'm thinking on 7 meters, could be bigger or smaller. Perhaps 7 meters is fine. And these are the old machines that we have there. This is the air tagger, a drum, pneumatic with a lever and just compressed air. The pulley is a standard pulley. You can do that even on the moon. If we get to the iron and so on, it's just cast iron. So we might need some materials and some crucibles and so, but eventually you may produce many of these on the moon. And the slusher itself, this is the workhorse of this work. This has to be heavy, but of course, 1/6 lighter on the moon. We need to know how efficient we could be. There's another one that I like. This is, I call it the moon raker, but it's a box basically to avoid the spillage and has rippers. So it can help to rip the surface if it's kind of hard. For NASA, the material behaves more or less like a hard ice cream. It's a soft concrete, a mix that was used, and they gave us specifications from the civil construction industry. And this illustration I want to show you because it's done with one of my students. Is an undergrad student who is collaborating and is showing more or less how it's going to be actually the thing. It's made the last week, so it's not vintage, but I gave the proper colors. So where is the material going to be dumped, and then how I'm going to move the drum and also the pylons for moving and pointing the slusher in different directions and other areas in where this is going to happen. So I want to honor this and also acknowledge his contribution to this work. For collecting the material, we need some sort of, I mentioned a mucking machine, but I like this because of the appealing, but of course it's hydraulics. We need to have a version for the moon. So I'm trying to use my AI engines and try to issue the questions and say how can I transfer these technologies to the moon. The threads are going to work, the bucket is going to be okay, can I work it from the mounting on it, and can I change the hydraulic for mechanics or chains or gears as we have seen recently. Another machine that is also proper and is not because it's vintage, but it's very strong and has gears and chains like a bicycle inside. I used to work with something like that, but it has also tracks, and I can use it on rough terrain. It's wider, and we can adapt perhaps easier this to the vacuum of the moon and switch the compressor for electric power. Then we have this. I love this. This is one of the first autonomous haulers that are available in the market. Is totally autonomous, but also we can have teleoperation. And of course, there are hydraulics. We can replace those with more mechanic components. Another question is, how can we get one for San Javier? Maybe we can talk with with the providers and get one. And the other one is the charging station. This is easy to, it's a simple infrastructure, and we can use Mylar and others and Lego bricks or similar to connect this to the charging station. Can we build a similar one in San Javier? So these are naive but kind of valid questions for the AI. And this is one of my favorite, the parasols. I mean, Tucson is super sunny, and we need this. When I walk on this Redito River, I need to stop here to meditate and to freshen up. So this is simple. There are rails and some Mylar things and hooks and things that could be done easy on the moon. I'm trying to also translate this to what we can build on the moon for the protection of the astronauts and the machines and others. Combining these technologies, also I would like to include modern things like a wireless camera, Wi-Fi. We need the Wi-Fi or the wireless network on the moon, and also in Tucson, in Zaguarita, and also the water wall barriers or sand wall barriers, whatever you want to use, easy to carry, cheap kind of, and they sell by 4. This is kind of the illustration of what will look in a profile illustration with one of the machines, and how the material will be dragged from one way to one stream to the other, and then moved here. I put a lever and sort of an astronaut to simulate what we're going to happen, and we can have camera, digital camera with solar power and so on. Another version of this alternative version has also the IoT sensors that I would like to add, like a sensor for cable tension, a sensor for the gear that or the drum power of the drum, energy, electric or solar, whatever, the weight that we're carrying, overheat, human health, important, and the surveillance of the observation of the operation, and the parasol for sure. This is a mock-up illustration, an animation of how will it look. I am assembling my parasol here for the operator, and then the first drag, the first scraping, the second scraping, the third scraping, and so on, and observed by the surveillance camera. And this is kind of illustration also transferred to San Javier when we do it here or around here, and this is the way it will look. And my dream hauler or something similar. Transfer this to the moon, may look more or less like this in a sort of a illustration of an excavation, and the same process. The road is baked regolith, so we are going to extract the regolith for baking it with microwaves and so on, and use it for the road. And this is one of the purposes of this. This is an inflatable that we have seen yesterday, and this is a airlock for entering there, and this is all the thing with some hatches buried in regolith. So we may still first use the regolith for this, and a similar machine that might be one of those contraptions that I was dreaming of for whatever use it is, with an arm and other things. These are the specifications. This is from Gersh from the NASA papers, and I try to put all of this. I suppress the ballistic transporters and foundry because I'm out of the presentation for that, and showing some of the AI questions. Very naive, very candid, very robot type, but some of them could be done, and we need to raise these questions for repeating this model in many areas of the South Pole. The monitoring of data analysis is just theoretical, but I would like to have a control room, the decision support systems that we're working, something like orange data mining would be, or some other. These are referential graphs, but this would be the analytics we may like to do, and some control room with the illustrations, surveillance, solar panels, machine health, human health, virtual reality, augmented reality eventually, the pit production, dashboard for that, and terrain updates. Here are some students measuring the future pit and later digital terrain. This is our own Mine Intelligence Research Group. I wish I could use this from campus to see what's going on in San Javier, but it's a work that is done by other specialists. And these are the reference I'm using, basically the work of Gersh from the NASA papers, David Lister's Mining on the Moon, very inspiring, and then Somariva, there is a nice paper from Acta Astronautica, one of our favorite journals for space stuff, that explains the economics of moon mining. You may have noticed in each one of the items I showed that there's a prize. It's because I'm looking for funding to do this in San Javier, and perhaps I get it from the provost, if not from the outside. If anyone is interested, the university is open to that. And some of the conclusions, this is from the vision of Richard Gersh. I just updated with what are the benefits of the things that I'm showing. Have fewer moving parts. They're simple repair. Simple is the common word here. Less inventory of parts, spare parts. We can 3D print some of them. And in general, is low, is cheap. We're going to start cheap. And that rusty machine, we can be painted and presented nicely for the moon. The name is called iLunars. And iLunars is because it's internet-based, lever-operated for the moment. It will be autonomous later, unconsolidated regolith navigational and retrieval scraping system. And I want to acknowledge three key people: James Werner, my former student and now director of the San Javier laboratory; Adam Arbizo, who is doing the work, the coordinator on the mine, at the mine; and Ethan Williams, an undergrad student who did that sketch of the concept that we're going to make it happen one way or another. Perhaps for next year we will show the results. That's everything I have for this presentation. I'll be happy to answer questions, if any. And thank you very much for your attention, and thank you for having me in this conference.
Thank you, Vito. Any questions to be asked in the audience? There is one in the chat room, but I kind of prefer talking. If somebody wants to talk, I'll put that forward first.
Oh, okay, very good. I have one here from Doc Plata. Good to hear you, to see you, Doc. I've seen you in the previous conferences. And well, for propellant, does it make more sense energy cost to harvest, polarize, or extract only the oxygen from loose regolith? I'm still not sure if there's a hope to extract the water if we find the ice on the regolith and extract it, decompose it quickly in oxygen and hydrogen. It was funny because in some of the papers we can find that they say, oh, we can have water by combining hydrogen and oxygen. So they might think at the beginning that we're going to bring them separate to the moon and do this thing for getting the water, which sounds like opposed to what we're looking for, but we still have the hope to get the water and do the work. I have some colleagues that are working on several ways of producing this and extracting in a way the icy regolith. There, I have a researcher who is doing a pipe or a column with some regolith stimulant and ice inside and extract it. But then the process of separation could be costly for the moment. So I will go first modestly on this type of work in collecting the regolith for the burial of the bases of the moon bases, and that will be the beginning. Later we're going to do things like the concrete or the water separation or so. So it might mean that at the beginning we may, excuse me, need to bring some of the materials or some of the material from the earth at the beginning.
Thank you, Victor. Great talk. Just wondered real quick, since I'm kind of like water mining. When you're slurry, is there an expectation to do some kind of a pH amendment in the slurry? I mean, seems like it could be a good point. Like if it's already to the point where it is moving, And I'm assuming it's not frozen when you're saying a slurry. We've got like a straight liquid water movement.
Yes.
Any thoughts to pH adjustments at that time?
Very good. Great to. Thank you, Colin, for your question. And also, I was great to hear in your presentation about copper and the leaching and and all that is kind of very familiar to us in Arizona.
That's where I learned it. Yep.
Oh, very good, very good. And
or
so
New
we
Mexico,
have.
but yeah.
Oh, excellent, excellent. There is copper from the oxides that we can extract using the leaching. We might reproduce the leaching somehow on the moon, but we might have some issues with the aeration or the extreme heat and cold and other things. The other is the flotation. I've learned that some people is trying to find things like that, but I don't know how much. First, I think there is almost or no copper on the moon. I cannot say that for sure, but if that is the case, copper will come from Arizona, and we in the way of electric motors, wires, and other things that we might require pipes at the beginning. So, but yes, for some metallurgical processes and perhaps other than copper or similar to that, we need to know how much we find this material, like oxidized material, if there's any, because the presence of oxygen is kind of significant now on the moon. We might need to do this, but we need to be sure if we're going to do it indoors as is expected, and what we will require for that. Some other things like melting or foundries may use the vacuum and the cold of the external environment to save some cooling time and things, but still I need to learn more about the pH regulation for these processes and how will they work. At the beginning, it has to be indoors, and according to that environment, we might learn what how much of pH or lime or whatever we require for regulating that will be used.
Yeah, there may be a borehole that's really deep that you essentially just push everything into and drops a couple kilometers until it gets warm enough to wherever that depth is to have liquid water. Would save an enormous amount of energy. So yeah, I agree, it would be indoors, and by that I mean way underground would be my expectations. But thank you, great presentation.
No, thank you, Colin. Thank you very much. It will be easiest to just ship copper from Earth. Yes, but if a later goal is fuller independence, then biomining or phytomining for copper may be the choice. I agree with that, Doc, and that's one of the things I always like. I keep forgetting the name of one of these books of people of humans in Mars trying to be independent from the Earth, and they try to capture all the shells that were orbiting around Mars and have an abundance of steel and titanium and other things and create their own economy. So it's a short novel. And I always remember that when we're thinking on the moon and what is going to happen when the first babies are born on the moon, and say, hey, that's not my my home world and others. Is there anything here like Philip, I have a question regarding thermal properties of your proposal. I read the biographies of Antarctic explorers, read that someone has been dragging us. Oh, yes. Those are things that, yes, are considered. And we are discussing this with James and other people. How are we going to simulate those problems? The Slusher looks good, but needs to be very heavy and many times heavier than on the Earth. And also it may not be appealing to some parts of the moon, which the material is harder. So maybe we're kind of collect first the soft part, which would be the 4 inches or so of powdery regolith, and then scrape a little bit more only where our the geologists will find the softer material, or then find a way of scraping or ripping that to make it softer and then collect it. In underground mines in real life, the slusher is used when you blast the rock in the stopes and the underground stopes, and the material is already fragmented. They don't want to break things, and that's one important thing that will be done. Okay, I think we are on the time, and if that is the signal.
Yep, that's
okay. Very good.
The egg timer indeed.
Excellent. Thank you again for having me here. And
oops, sorry. Sorry, I didn't mean to mute you there. I need to. I want to.
Oh, sorry. It's okay.
Can you just unshare the screen?
Yes. Oh, yes. Bye. Thank you very much.